my computer, and then that's that recording now can go up on Moodle or on the blog, or it can go on both. I've got a little section already for chapter 8, and that's I think where I would post this video for people who couldn't make it, or for people who just want to go back and take a look at what we talked about. So just first briefly, our new schedule is a little different from the old one. It's going to rely a bit on you keeping on top of things yourself a little bit more. It means reading a chapter over the weekend and coming up with your questions about material you're reading. Doing that PCCI, which from this point forward is going to just be those stop and think questions. Then what you need to do next is practice problem solvings and discuss questions that you have. And so that's what I want kind of the rest of the time we spend together on Mondays after the mini lecture through Tuesday, Wednesday, Thursday, and tutor time is time for you to practice solving problems and doing it sort of in a space where there's somebody to ask questions of when you get stuck. Okay, whether it's a fellow student, an LA, myself, Travis, a tutor, whomever. So that's why we've expanded a number of different hours. There'll still be a weekly homework done on Wednesday, due on Wednesdays, and we'll give you feedback there. You can also, of course, look at solutions that other people have posted for other problems and see what their feedback was for the problem maybe that you didn't submit, but that you did and you want to somehow see some feedback on. So one little housekeeping item is that the graded quiz 6, the one that many of you took on paper on the last Friday we were together, we scanned those in. There's a link in the quiz section on Moodle for quiz 6, and I think the title of it has to do with taking it on paper. That can be found on Moodle. In fact, I think I have it up here. I can go behind and get us to there. It's this quiz 6, returning those taking the quiz on paper. There is a quiz 6 electronic version. That was for people who didn't take it on paper and took it between last Friday and now. So don't feel like you have to go take it again or anything like that. I wouldn't count it against you. If you want to practice, take it. But that's why there's 2 quiz 6 links. But you should go there and you can get your quiz results at that link. Okay. So now I want to go back to here. Okay. So the sessions are going to be recorded. I'll post the video on Moodle and maybe on the blog if you like it on the blog. What's nice about the blog is you can have a running bunch of comments on the video. So if somebody posts a comment on there, Travis and I will see it, and maybe we can address something that if there's a question. So I'm going to start on the afternoon sessions. I'm going to start with a very short lecture review, and I'm going to focus really on the big picture kinds of things and questions that come up in your reading. So I really do look at your feedback to the PCCIs. And I really want this part to be about 20 minutes or less. So today, that's going to mean we'll go through some PCCI questions because a lot of people had questions about some of those PCCI questions, okay? And then I've got some other Chapter 8 practice problems, and we can do those basically as long as people want to hang out. But I have to go around 4. So if we go past 4, it might get a little more lonely. But this room is your space. You can also stay here as long as there's anybody here to work with. While I'm doing this little mini lecture, questions are really welcome. Do be patient. This is my first time doing this on Zoom. And if I'm not looking at my laptop screen, I won't know that you've asked a question necessarily. So what I would really like Karina and Jack to do is when you see questions coming up on the chat and I don't see them, go ahead and unmute your microphones and let me know that there's a question, especially when I get to a pause and there's a good place to address a question. Okay.
Good.
If you're having any like Zoom difficulties, definitely put those questions in the chat. I might not see them, but Jack and Karina would see those, and they might be able to help you get settled rather quickly. Okay, so I might not always be looking at your questions, so thanks in advance to Jack and Karina for helping out on that. Okay, so let me go forward one. So there were some questions about the course structure. One of the questions I got was, are the Q&A sessions mandatory? And I would have to say, it's not mandatory that you attend them. It is your responsibility to be able to solve the kinds of problems that we'll talk about today, problems that are like in the PSS, problems that are in the PSS, which are posted now. I also posted another set of little short and sweet concept questions, in the chapter 8 area, because someone had asked, hey, can I have some more questions like number 5? So I made a little set of 3 from figures I found in the book. So they're not mandatory in the sense that I'm not going to mark you down on attendance or something like that. If you are finding it better to kind of work on your own time and then be in touch with questions, that would be certainly a fine way to work. But if you're the kind of person who kind of needs other people around to help keep you on task, then I'd say make it a regular part of your schedule to be here for however long it is useful for you to be here. And use this time to do some problem solving. So we're letting things other than Monday be pretty asynchronous. We'll be here to answer live questions though during any of the times that are posted on the new little schedule at the top of the Moodle page. Another question was about how will problem solving session participation work? And well, some of that I hope is going to be answered today when we do breakout rooms. I can put, say, 2 to 3 people in a breakout room together, and you can work on a problem. You can share a little whiteboard space together, or you can work on your own paper and then show that paper up on your camera to your partners. I'm not going to dictate to people how they share in the breakout rooms, but there's a couple different ways to do that. And you'll be free to travel between a breakout room and the main room. And people like myself, Travis, and our LAs will be free to travel among the various breakout rooms, so that we can check in on you every so often to see if you have questions, or you can go out to the main room and say, hey, I have a question. And I'll send somebody there to help out. As far as the course goes, those were the main questions. I did sense there was some general angst, or maybe that was me feeling the general angst about trying something new, but I feel comfortable with all of you that you'll all email me with questions, or let me know what's working, what's not working, what we can improve as we go along. Does anybody have right now any other questions regarding the course and the course structure from here on out? I take it you all know how to raise your hand in that participants box, or if you have a question, put it in the chat. So I'll give you a minute to let me know if you have some questions. Okay, I don't see any right now. I guess that means that the PDF we sent you was just crystal clear and just really well read by everybody, so I appreciate that. Okay, so the PCI questions that were about physics. There were several people who asked about reference frames, about inertial and non-inertial reference frames. And that always comes up with circular motion. More so than it does when we were doing, say, straight line motion or projectile motion or things where you're using an XY coordinate system. Just to remind folks, an inertial reference frame is one that is not accelerating. So for example, a car that is screeching to a halt, from the point of view of the driver is accelerating. So the driver is in a non-inertial reference frame because they're accelerating. But the person on the sidewalk who's watching the car screech to a halt, well, they're in an inertial reference frame because they're not accelerating, but they're observing, say, the driver, or the groceries on the seat next to the driver, or the antiques in the back of the truck. Whatever they happen to be observing, they're observing something that's accelerating, but they themselves are not accelerating. And the important idea there was that if we're going to draw free body diagrams, and if we're going to use Newton's laws to solve problems, then we'd better darn well be in an inertial reference frame, okay? So to me, that's the big important thing. If you put yourself in the reference frame of say the accelerating driver or grocery bag, or in our case, a rotating, an object that's in orbit or rotating around the center, then you won't be able to apply Newton's laws in the same way that you normally do. So I mostly advise against being in the non-inertial reference frame because it just gets really confusing. I don't mean to say that there's no place in this world for people who will look at things in a non-inertial reference frame. It's not something we do much in intro physics though. So we can chat more about that when we're not in the big group if you're really interested in non-inertial reference frames. But for the most part, I'm going to ask you in this class to get out of the accelerating reference frame, get yourself, look at the problem from the point of view of someone who is not accelerating. And you'll do a much better free body diagram that way. And I think you'll do better at problem solving. For the stop to think questions, number 2, 3, and 5 seem to have the most questions. So I think I want to go through those ones each by themselves. I did get a question about the water in the bucket, that is kind of a confusing discussion. And I agree that's confusing. I'm not sure there's something I can do right now in front of everybody to make it less confusing. So that might be a question I'd like to follow up with that one student one-on-one. But if other people are interested, let me know. So there we go. Okay, good. Thanks, Travis. Do we have any other like big picture questions about the physics that you want to make sure we address in this little intro mini lecture? Give people a moment to respond to that. Okay. All right. Well, I'm just gonna then get on with the show here, and there we go. I'm gonna put this in a different location. I think that'll be better. And maybe I'll be off screen for a little bit because I think I'm gonna stand up to do the mini lecture portion. Okay. So. Okay, so my plan here is to just do a really quick review of the chapter 5 through 7 stuff, kind of the big picture stuff to remind you of stuff that we learned from the first half of the semester. Then I'll do just a quick review of circular motion from chapter 4. And then how does that circular motion fit into kind of the big picture here? And we'll kind of go into questions. And I'll give you some problems to work on. Okay, so you might recognize this slide from before. Kind of the big picture about Newton's laws and problem solving is that we learned how to make essentially two different kinds of diagrams. We learned to make a free body diagram and a motion diagram. And the free body diagram was all about forces, right? The free body diagram was all about forces, and the motion diagram was really all about acceleration. The whole point was to figure out the direction of the acceleration for particular objects so that you knew something just from the description of motion about the acceleration. Okay, and the free body diagram, really the most important thing about it was that there was a net force, and that net force was going to be related to acceleration through the mass, okay? So the things you're really good at now are identifying forces on an object and figuring out what do you know about their acceleration given the description of motion. Okay, so those are two skills that you've practiced and you're good at. We're going to use those two things to relate forces to acceleration with Newton's laws. And you've done that a lot in chapter 5, 6, and 7 by basically writing what I was always calling Newton's second law equations. And you would generally do this in both the x and the y direction. So you'd have like the sum of the forces in the acting in just the x direction was equal to mass times acceleration in the x direction. You had to be careful about signs, you know, depending on what your coordinate system was. You would also do the same thing for some of the forces in the y direction, only that was related to m-a-y. And for some problems, the acceleration was 0, and you could say all the forces in the y direction must cancel out. Sometimes that happened in the x direction, sometimes not. But those were some fundamental starting points, right? Often this was a place to kind of assess how many equations do we have and how many unknowns do we have? And do we already have enough information to solve the problem? And sometimes you did, sometimes you didn't. And if you didn't, then you needed to use other models and relationships. So for example, sometimes you had to use the model for friction, either static friction or kinetic friction. And sometimes you actually had to make some assumptions to figure out which friction was the right one. We also did some problems with the model for drag. We mostly did those computationally. Then what were some other things we did? Oh, sometimes we would have multiple free body diagrams where two forces had to be equal by Newton's third law. So I'm going to just put Newton's third law here as something that helped us relate forces from one free body diagram to another. And then the last thing I think I put here is often we had to use things like kinematics, because kinematics sometimes, you know, we're not always going to give you the easy way out. We might tell you things about the position and velocity and time, and it's enough for you to figure out the acceleration. So sometimes this is basically information in the problem might help you figure out, say, the acceleration, whereas these models and Newton's third law may help you figure out relationships among different forces. Okay, so that was kind of the big picture, and that's kind of where we left off when we were so rudely interrupted by the coronavirus outbreak. Okay, so that's what I think of when I think of as the big picture. Okay, now for circular motion, I'm going to really emphasize in this review the velocity and the omega, because I think those are the ones that are probably the most unfamiliar. So if I've got this is called a circular pendulum, where this ball is basically tracing out this nice circular path. We could talk about that ball going in a circular path would have an angular velocity, an omega, which is basically the units were radians per second. So that was kind of telling us like how much of an angle does it pass per second. And if it was going one complete turn around, that would be 2 pi radians in whatever time it took. So one way of thinking about this is that omega, it goes 2 pi radians in one period of time, where I'm using capital T to mean how long is one rotation. How long does one rotation take? Right? And you could think of the same thing for the velocity, that the velocity of this ball as it goes around a circle. The circle's radius here, I'm going to draw that in as a big R, okay, that it travels the whole circumference, right? It travels 2 pi times R, during that same period of time, right? So you can use kind of your intuition there to figure out, oh, okay, what is omega in this case? Remember, often omega, they'll tell you in things, units like revolution per second or revolutions per minute, okay? And often for problems, we want to convert that back to radians per second, but some problems you could possibly use those units. For velocity, that's still going to have our familiar units of meters per second, just like we've had all along. So I want you to be really comfortable with both these terms for velocity and omega. And if you notice that velocity and omega, those equations actually look very, very similar. That this velocity, this little part here is 2 pi over t. That's 2 pi over t. That's the same thing as omega. So I can say that v is omega times r. Okay, and I think your book may have come across this in a different way. But if you know the speed in meters per second, you can usually figure out omega. If you know omega, you can usually figure out the speed at a particular distance r. Okay, so those are two really, really important things for uniform circular motion. And then I think I might need to add a little slide in here because I didn't leave myself enough space. And let me bring maybe I'll bring that, this one over. Oh, can I bring that over? No. Let me just draw in that ball going around in a circle again. Whenever you have circular motion, and here, uniform circular motion, you'll always have some sort of acceleration towards the center, which is what centripetal acceleration is. I think back in chapter 4, we called it radial acceleration. It doesn't matter, either one can be used for that. And that was dependent on the speed. So that was v squared over r. But you could also write that in terms of omega. It would be omega squared times r, okay? And that was if the motion was uniform. That just meant in this particular situation here, you would always have some kind of acceleration. So if it were moving, say, if its velocity, say we're coming kind of toward me here, then the acceleration is towards the center, okay? And the magnitude is related to the speed at that particular point. If it were speeding up, you would have another component to your acceleration. There would be a tangential acceleration if you were in non-uniform circular motion. Circular. I'll use the traditional spelling of circular here. Okay. And that tangential acceleration, it tells you, are the RPMs getting bigger or smaller, say. Okay.
Is that AC or AT?
This one is supposed to be AT.
Okay.
Okay.
Thank you.
Oh, thank you for asking. Okay. And so if this were getting faster, say, in the direction of the velocity, then I could say I've also got, in here, and I'm going to draw it off to the side, just so that it's not on top of everything else, I might have a little bit of tangential acceleration. Okay. And I'm going to look at this and I'm going to say, well, that tangential is perpendicular always to the centripetal acceleration. So AC and AT are perpendicular always, just by way of geometry. Okay, they're always perpendicular. And so just like when we had problems with the X and Y direction, we could treat the X direction independently of the Y direction because they were perpendicular. We're going to take that same approach here. We're going to treat the radial or centripetal acceleration as one component, the forces that are keeping it in circular motion. We can write one set of Newton's laws equations for that component, and then the tangential acceleration, we can write a different set of Newton's second law equations, kind of like we do for X and Y in the linear world, so to speak. So if I go back to my big picture, how does this circular motion fit in? We're still going to be using free body diagrams for our forces, and we're still going to be using motion diagrams to sort out the direction of our acceleration, okay? We're still going to be relating forces to acceleration. But here, when we go to write the Newton's second law equations, we're much more likely to be doing some of the forces in the R direction is equal to M, A, C, for example. And if necessary, some of the forces in, say the tangential direction are equal to M, A, tangential. And I'm going to put one more in here because sometimes it's needed. The R and the T came with a Z. There was also, they're kind of fundamentally three-dimensional problems in a way that our other problems were not. So some of the forces in the Z direction could be M, A, Z. All of the examples I can think of that this is zero. Okay, like for example, if I go back to that pendulum, what I would say is here, my Z direction is up. And if that's circling around in a flat horizontal circle, then it's not accelerating in the Z direction. That's what I mean by often the Z direction is going to have zero acceleration. But it will depend a little bit on what you call the Z direction. So I don't want to say that it's always zero. But let me say many times. And sometimes that information is useful, right? Because it was useful sometimes to know if an acceleration was zero, then you knew that some forces had to balance each other. Okay? Now, are we going to have to use other models and relationships in these kind of situations? Oh yeah, and it's going to be the usual cast of characters here, especially the friction model, potentially the drag model, though I don't think I have an example today where that would come in. We may have to use Newton's third law. We may have to use, well, what we know about the motion. So specifically, that centripetal acceleration is related to speed. Is going to be something that will come up again and again and again. Okay, so it's a little tweak on what we've been doing before, but what I really want to emphasize is the part that I think you'll need to get used to the most is drawing these free body diagrams in this RTZ coordinate system. I think that's one of the hardest things to get used to. So let me pull up that picture from the text to clarify that. RTZ coordinate system means you take the point of view for a moment of that particle that's in circular motion, and you put your R-axis pointing toward the center, and you put your tangential axis going in the direction that the object is moving, and then the Z-axis will be whatever is perpendicular to both of those. And the Z-axis may or may not play an important role, but it's there. Okay, so we've got to start to get kind of more happy with or familiar with this RTZ coordinate system. Okay, so I guess the first thing I wanted to do was this. I got this little ball at this particular location. I've also got a little windmill here, and you can imagine that the windmill is actually rotating at some angular velocity, omega. Let's let this be rotating also with some angular velocity omega. What if we were to try and draw a free body diagram of this ball? You know, what point of view would we choose? Because if we're really thinking about R, T, Z, that's sort of three-dimensional. What point of view would we take when we do that, a free body diagram? And there's not one answer to the question, but let me give you a moment to think about it. And now think about, how would you draw a free body diagram for that ball in the conical pendulum? How would you draw a free body diagram for this little piece of bubble gum that is stuck on the windmill blade? How would you draw, like what coordinate system would you even use so that you could look at the forces that are acting there? So I don't think I want to go to a breakout room for this. I want you to think about it for a moment. So I'll give you a minute. And if you have a candidate for a free body diagram, then I'd say raise your hand or say something on the chat. And you might have to just put your free body diagram up on the up against your camera to show me. But if you can do that, let's see some candidates here. Okay, I've got a lot of people not using the video at the moment. Hopefully, if they've got some free body diagrams, though, they'll be willing to turn on some video. Or if you have an idea and you're not using video, you can use annotation. But we can't, I don't know if we can go crazy and have everybody annotating all at once. Okay. All right. So now that you've had a couple minutes to think about it, can somebody share a little bit of what they're thinking about for a free body diagram for, let's say, for this ball over here on the conical pendulum? What point of view would you be looking at that and asking and saying, well, here's my free body diagram from this point of view?
We have a hand raised. Serena?
Yeah, Serena, good.
Yeah, I don't know if you can see this okay, but.
Oh, okay, I'm gonna make it so I can see it better here. Okay, all right, so what I'm seeing are two free body diagrams.
Yeah.
And I can't quite read, there's the one on the right is the actual free body diagram with forces. Right?
Yeah, I tried to define the coordinate system, I think to the left. Yeah.
Oh, okay, and I see two forces on the free body diagram.
Yeah.
And one of them is labeled T, and one of them is labeled F. Is that D or at the bottom?
FG.
FG.
Yeah.
Okay.
I'm realizing that the tension should be at an angle, but it's the same idea.
All right. So, okay,
Yeah.
so interpreting your diagram, you're saying, well, if I've drawn the free body diagram here, then I'm going to have FG pointing down, and then I would have the tension at some angle here. And that would depend, of course, if I were to label this angle theta, then you'd be able to come along here on this free body diagram, and maybe I'll draw it a little more closer to what I've got up here. Okay, that there's a tension force. Okay, and so for this one, I would say the point of view that Serena chose to use was it's as if she's looking at the ball coming toward her. So she's looking like, here's the z-axis, right? And here's kind of the r-axis, and I'll use those in a different color on the picture. So kind of here's the r-axis, and here I'm trying to draw it perpendicular, and here's the t-axis, and here's the z-axis. So when we draw the free body diagram, we can often only draw it in 2D, and we kind of, you know, have to either not put forces on that are acting in the perpendicular direction for that. Okay, how about for the other one? For this piece of gum that is traveling in a circle as this windmill goes. Do I have anybody with a, oh, how do I unpin? Well, I'll have to, there's my technical problem for the day. Let me go, yeah, there we go. That's how I unpin. So does anybody have an idea for how you would draw the free body diagram for the bubble gum, or a candidate that we can talk about? And this one might be a little bit harder because I didn't write any RTZ on it before. So it might be good to kind of say, well, which direction is R, which direction is T, which direction is my Z in this case. I see a hand up. I see Nestor. So Nestor, what have you got?
So I don't have it all figured out, but I'm wondering if in this case we have air drag acting on it. And
oh, yeah, we could have air drag acting on it, sure. And if it's located right where it is on my screen, what direction would air drag be?
I'm not quite sure.
Ah, okay, yeah, that's a good, so for the moment, yes, we could have air drag on it, and we'd have to figure out the direction for the air drag, and especially for a windmill, it's probably going fast enough that air drag would be important. So let's keep that air drag in the back of our mind, and we'll have to figure out its direction. Does anybody else have an idea for that free body diagram of the piece of bubble gum? Why don't we do it this way? If I'll be generous, I'll start you off with a dot.
You have a hand raised.
Tell me a force. Now Nestor started with the drag force. And if it's really sitting here, then I would say that that particular piece of gum at that moment has a velocity vector that's going straight up. So if the velocity vector is going straight up, what direction is the drag force going to be going? And anybody can unmute their microphone and chime in.
We have a hand raised from Anna.
Oh, Anna. Go ahead.
Yeah, I just wanted to have some input on like trying to figure out the free body diagram for the gum.
Uh-huh.
And yeah, so I'm thinking that maybe we have a normal reaction since the gum is like stuck on the blade, but I'm having a difficult time trying to figure out the coordinate system as to what it would look like.
Oh, yes, exactly. Well, let's take a step back then. If you were this piece of bubble gum, what would be the R direction for your coordinate system? And I recommend starting with R because R is usually the easiest one to figure out. So for this one, if it's going in this circle, the radial direction is always toward the center of the circle. So I'm going to change to green for my coordinate system, that my R axis is definitely pointing inward. Okay, and then usually if it's going in a circle, you can figure out the tangential direction by looking at, well, what direction is it going in the circle? So here, the tangential direction, and I'm going to scooch it over just a little bit, my t-axis would be in the same direction that it's traveling. So the z-axis, where is the z? Oh, the z-axis would actually be coming out of the board or into the board, I suppose. I would accept either one of those. So we're kind of looking at this whole problem as if we're looking down the z-axis. Okay, so if we've got this R and this T direction going, can anybody tell me one force that's acting on there? Say the drag force. Nestor, have you figured out which direction the drag force is now?
Joyce, we have comment from Piper in the chat.
Oh, okay. Oh, okay. So someone had said there is going to be static friction toward the center. Okay. So I'm going to put on here some kind of force due to static friction, whatever it is that is holding it in place. And you might as well call it static friction. It'll be a lot because it's gum and it's really sticky. So that should have a lot of friction. So you've got static friction pointing towards the center. Does anybody else have another force that should be on that free body diagram?
There was a clarification in the chat that the static friction and towards the center were two different answers. So there's static friction, but not necessarily towards the center.
Oh, okay. All right. Well, if there's, let's talk about static friction then. What direction should it be? So, yeah. So that would be like whatever is causing it to stick on the blade. It's got to be some direction. And so what direction would it have to be to make it stick on the blade? So I've got something from Helen. Is it in the Z direction? The direction opposite the F push. Oh, this question is opening up a lot of good questions, isn't it? Well, can we start with an easier question, an easier force, like one that is put on pretty much all the free body diagrams we're doing? What direction is the gravitational force? Okay, I saw that, Heather. Yeah, so gravitational force. So we've got all of these things happening. And remember, now when we do free body diagrams, the idea is we kind of, we wrap a little surface around the object, which is the bubble gum in this case, and any forces acting on it have to either be something touching the bubble gum or a long range force. So we've got a long range force there, right? And since it's stuck to a surface, we have two possibilities. We can have a normal force perpendicular to the surface. Normal to this surface would be like out of the board, so we're not going to see it on this free body diagram. But we would also have some sort of a frictional, or you could call it a sticking force on there, right? And what do we want to call that sticking force? Well, we can call it friction. I'm not going to take this problem any further, but what direction should that sticking force be? And that, to me, is the conundrum, right? So, if we have, and if we have drag, that was the other one. If we have drag, since the velocity is going up, wouldn't there also be a drag force going down, right? Pushing, if there's air pushing hard enough on that piece of bubble gum, that drag force would be going down. So this looks like it's something that's going to be at least accelerating downward, but we know it's traveling in a circular path. Okay, so what do we know about the motion? We know about the motion that it must have an acceleration that's to the left. So over here, I'm going to write, I know my F net has to somehow be to the left. So this sticking force, whatever it is, I have to, if I add it to these two downward forces, it's got to give me something that's going directly left. So I would have to say that sticking force would have to be something like this. Like as that bubble gum is going around, right? Newton's first law might want it to go straight, but it needs to stick. So that sticking force is pulling it along with the blade. It must be pulling it up a little bit, but it's also pulling it towards the center. So this one is what I would label a really hard problem to solve, but it brought up a lot of questions about, remember from chapter 5, 6, and 7, when you're making a free body diagram, you can only count forces for things that are touching or the one long range force we have. After that, there's no more forces on the free body diagram. The free body diagram you have with the forces you identify has to explain the motion, okay? Why don't we try an example that's not as hard as this one? Oh, and I wanted to go back to the to the PCCI questions before I get to this question. So let me pull up the PCCI question because let me go back to here and I'm going to go in and I'm just going to pull up the PCCI in my preview mode and preview. Where are we? Preview. Come on. Oh, here we go. Continue the last preview. Okay. So let's switch gears a little bit. And here I might want to have you ask each other some questions. Sorry. Number 2 is what we had a number of questions about. CCI. Stop and think 8.2. That's this one, right? So we're trying to rank these things in order from smallest to largest. What's the centripetal acceleration of these particles? Okay, so here, what I think we have to do, I'm going to take this back to Notebook so that this shows up in our slides. And take a look at this. Now that we've reviewed the circular motion and we're asking about acceleration, what kind of acceleration do you think we ought to be looking for here? Would it be the tangential acceleration or would it be the centripetal acceleration? Yes, someone has put in centripetal, some people have put in AC, AR, so a number of people on the chat are saying, yeah, we should talk about centripetal acceleration. And remembering that that centripetal acceleration was v squared over r or omega squared times r, either one is okay to use here. What would we figure out for the accelerations here? Well, for A, we've got whatever, I don't know what the velocity is, but its acceleration in case A will be v squared over r. In case B, then the acceleration for B, well, that's going to be double v squared over r, which would be 4 v squared over r. For C, and I'm sorry, I'm getting a little out of alignment there. For C, I've got v squared over r. Again, that's really the same thing. Even though this velocity is maybe in the negative direction, I still get v squared over r. And oops, I shouldn't switch to capital R, sorry. Okay, so that's a little weird. And someone did ask about that. They asked about these two cases, especially because the velocity is going one direction and in the other direction. Are those centripetal accelerations the same? I'd say that's a very good question. So would their centripetal accelerations be the same? Well, let me think about that. If I were in this situation, the velocity just before this would be kind of that direction. And I would need an acceleration toward the center to get myself into line and stay on that circular path. Over here, the velocity right before that was kind of this direction. Well, I would need an acceleration kind of that's towards the center. That's going to get me back on that path. So yeah, it doesn't matter which direction it is going, whether it's going clockwise or counterclockwise, centripetal acceleration always points to the center. And that's not necessarily obvious or intuitive, but that is indeed the case. Okay, for situation D, then we would have v squared over 2r, so that would be like 1/2 times v squared over r. And then for case E, acceleration in this particular case would be double v on top squared and 2r on the bottom. So this numerator gives me 4v squared divided by 2r, and one of those 2's would cancel out, and that would give me 2 times v squared over r. So when we rank them, it doesn't matter what v and r are in numbers. Whatever those numbers are, this one is going to be the largest. So b should be the largest. Next largest should be e. That's got a factor of 2 in front of it. So e is next. And then a and c actually have equal size, don't they? And in the instructions it told you if they're equal in size, put them in alphabetical order. So I'll do that here. So then I'll say next is a, which is equal to c. And then last but not least, well, actually last and least really, is d. Okay? So that was the reasoning on this kind of problem. And it won't be the last time that you'll be asked to rank something, I suppose. Let me get the next problem that people wanted to review from the PCCI was this one, the one about the turntable. So we've got a frictionless turntable, and there was again ranking the tension acting on the blocks. So here you have to imagine there's a string now, and so this string itself is going to have some amount of tension, and that tension pulling on that block is what's keeping it in circular motion. Okay, so as I'm looking at this one, let me just take that. I'm going to pull a screenshot out so that we can write in the smartboard land. Okay. So block on a string. What would a free body diagram look like for this particular object? Okay. So here, if I'm looking at this, I would definitely say that this would be my R direction, this would be my T direction, and the Z direction would be out of the board. So if I were drawing its free body diagram here, and I'm actually going to tilt this a little bit. If I were drawing its free body diagram, I would say I'm going to bring this object over so that the T direction is this way, and the R direction is to the left. I would say the only force I've got there is the tension. Now, does that mean that there's no gravity or no normal force? I'd say not quite, but just those are acting in and out of the board. I could change this and say, let me look at this from the R and Z direction. In that case, I'd still have tension pulling me towards the center, but then I'd have a normal force, and I'd have a gravitational force also acting, right? It's just that those two forces in this coordinate system would not be very visible in a 2D diagram, okay? So I would accept either of these two free body diagrams as being good descriptors of this particular object looked at from two different points of view, okay? What's happening in the Z direction is maybe not that exciting because it's not moving in the Z direction, but it does have acceleration in the T direction. So the idea here would be, let's use Newton's second law, sum of all the forces acting in the R direction, which in this case, there's only one, there's the tension. That would be equal to mass times that centripetal acceleration. And I'm going to do a very small amount of algebra with the eraser. That would be m omega squared times r. I could also have said m v squared over r. But for this particular problem, I was given omegas. So I thought, well, let me use the form of centripetal acceleration that has omega in it, that might be a little more useful here. Okay? So for this one, I'm thinking for A, that this tension would be m times our 50 RPM squared, and then times our R, which is 100 centimeters. Okay, and I could crunch that out. I'm not going to crunch it out at the moment. B would be same mass, because these were all for the same mass. Only this time omega is twice as big. So I'm going to write that in a, might seem like a funny way. I'm going to say 2 times 50 RPM squared, and then R is the same thing. R is 100 centimeters, okay? And I wrote it this way because now I can say, well, that looks just like the one above, except for this factor of 2 squared. So this is definitely going to be 4 times the tension in the case of A. All right? So you see where I'm going here. If I go to C, and maybe you can do this ahead of me on your own papers, it's going to be mass times, well, I've got the same omega. No, I don't, yeah, I'm sorry. I've got that same double omega. So 2 times the 50 RPM squared. But I've got a smaller radius. So I've got 100 centimeters divided by 2. Okay. So I can take that 2 squared and then divide it by 2. Everything else was in the original TA. So this one would be 4 halves of TA. That would be, sorry.
Joyce, we have another question from Serena in the chat.
Yep.
Where is the t-axis on the second, in parentheses, bottom coordinate system?
Oh, that's a good question. Here, that coordinate system would be, if I'm looking at that particular point, if I'm looking from this point of view, if that's where my eye is looking up at this problem, then T would be going into the board. Okay, and if I had a 3D model, I could do a better job of it. But the t-axis would be going straight into the board, and sometimes that's people put a little square with an X to indicate an axis is going into the board. So I could indicate it that way. Okay, but if we're thinking of uniform circular motion, not much happening in the T direction. Okay, all right. So I'm going to move from here up to the corner because I'm running out of space. I've got, for the case of D, then.
Bruce, we've got another question.
Another question? Sure, shoot.
Yeah.
Yeah. On the chat?
Yeah.
So what would we say is the general F net equation for circular motion? Oh, well, what a good question. I'm not sure that there is a general F net equation. In this particular situation, we figured out what forces had to be acting, and we figured out that it was accelerating towards the center, so we could identify in this particular case that it was tension. But that won't be the case in every single problem. That sometimes it'll be friction, sometimes it'll be a normal force, sometimes it'll be a combination of more than one forces added together, or the R component of something added to some other force. So there isn't really a general one. But what you can always do is when you're taking the sum of the forces in the radial direction, you can always set them equal to mass times the centripetal acceleration. So I'd say that this right-hand side, that one is going to come out a lot in your circular motion when you're dealing with forces along the radial direction, right? But what's on this side, the left-hand side of the equation, that's going to be different in every single problem. And that's something that it's going to take a little time to get used to that. Okay? Does that help, Cassandra? Okay, great, great, thank you. Are there other questions? We'll run through D and E real quick, because I think there were also a lot of questions about one other problem.
There's a question in the chat.
Okay. Where did the 2 come from again? Oh, I was using up here that in the first case, omega was 50 RPM, and I treated this 100 as equal to 2 times 50 RPM. So I was substituting in for 100 as 2 times 50. And every time I saw omega was equal to 100, I put it in as, say, 2 times 50 RPM. And over here, when we get to D, this is going to be 4 times 50 RPM. Oh, that's got to be a big mess. Okay. I don't have to do that. If you wanted to do this whole problem and put in all the numbers and crank them out, you will get exactly the same result. But my way of doing it was one way of kind of showing that you don't have to necessarily know the numbers themselves, but if you know the relative size of the omegas and the R's, you can figure out the relative size of the tensions without knowing the absolute size. And sometimes that's called proportional reasoning. And it's something that I hope you'll get better and better at as you study more physics, and especially in your engineering classes, you'll use proportional reasoning a lot if engineering is where you're heading, okay? So let's finish this one up real quick. The tension for D was gonna be mass times, this omega is 4 times the original, okay? So 4 squared times the original 50 RPM squared, and then I don't have enough room there. I've got to multiply that by the radius R, but the radius is only half, okay? Times 1/2 of the radius we had to start with, which was 100 centimeter. So for D, that gets us 16/2 equals 8 times the tension we had in the very first one, okay? So E is actually very similar, only the radius is cut down by another factor of 2. So I'm gonna leave this for someone to figure out. T in the E case has got to be half again, right? Because that R is half again. So there's 16/4, so that would be 4 times TA. Okay? I'm feeling like I might have made a mistake. Let me double check my work here. Omegas, oh no, it's in omegas, right? I think I understand. Okay? So now for this one, you would take your results, either your numerical results or these results in terms of how many times bigger than the first one was it, and you'd go and rank all of those and get to the answer. Okay? Are there questions about this one before I go on to the question 5? Okay. Alrighty. So then go back to this page, to my preview page, and go to this question. Okay, so I've got a car that's out of gas, that's rolling over the top of a hill with a speed V that's given here in green. And they're asking about what's the normal force and the force due to gravity. How are they related? Are they the same? Is this one of those cases? Or is it one of those cases where the normal force is not the same as mg. Remember, we had a big discussion about this. Is the normal force always equal to mg? And in the end, does anybody remember what we said the answer to that question was? Is the normal force always equal to mg? And can I see with a nodding of hey, I see a very distinct, no. No, it's not always equal to mg. You almost always have to use Newton's second law to figure it out. And in fact, I can't think of a situation where you don't use Newton's second law to try and figure it out. So nicely on this problem, they already gave us kind of the relevant free body diagram here, really concentrating on the y direction. They've got a long range force and the normal force here. So if we were to write our Newton's second law equation, we'd say the sum of the forces in the y direction, which would be the normal force, which is pointing up, and I'm going to say minus mg, which would be the gravitational force pointing down, so I'll use magnitudes here. Then that's got to be equal to mass times acceleration in the y direction. So it's really critical here to know what is the acceleration in the y direction, and is it 0? Okay. So is the acceleration in the y direction equal to 0? And that might not be very obvious. I'm seeing some heads shaking no, and I specifically see Anna's head shaking no. So Anna, why do you say so emphatically and without, without any doubt, I think, on your face at least, why do you say that the acceleration in the y direction is not equal to 0?
Okay, I think it's because the car is going over the top of a hill, but the shape that we can see here, we can see the hill is sort of like a cone of a circle, like a part of a circle.
Okay.
Yeah.
So if I dotted in a little circle here, whose radius was too big to even fit on my paper. Okay, this would be a circle, and I'll use change colors so I can say there's a circle. The circle that it's traveling around, and I'll just label it over here, has a radius. Now that has a radius r, and it's going at some speed in a circle, right? A moment before this, its velocity was kind of going up a little bit, and a moment after, the velocity was going down a little bit. So there needed to be a force. Need to have some acceleration happen in order for it to go from pointing up to pointing flat to eventually pointing down. As remember, velocities, getting flustered here myself. Acceleration's not about what the velocity is at any given point. It's about how the velocity is changing. What was it before? What's it going to be a moment after? So here you would be absolutely correct to say that that acceleration is not 0. I'm going to take away the green because it's in my way. There we go. So that's definitely not 0. But if it's traveling in a circle, and that circle at this moment, the direction towards the center of the circle, the r direction, is coinciding with the y direction here, then this is my old friend centripetal acceleration, A to C. Okay, which would be mv squared over r. Since they've given me some velocity information, then I could say that's what the centripetal acceleration would be times mass. So we're saying that the normal force minus mg is equal to mv squared over r. Now I've got r is coinciding, r is coinciding with the negative y-axis. So that might mean that I just realized I have a typo here. N minus mg equals mv squared over r, but that's actually pointing down. So in this coordinate system, I had better put minus sign there. Okay, so if I do a little bit of algebra, then to get n by itself, n is equal to if I put mg over on the other side, minus mv squared over r, it means that the normal force is the same as the gravitational force minus a bit that depends on the velocity. So in order for that to be true, that normal force has to be less than the force to gravity. Okay, so on that problem, that was choice B. Okay, and try this sometime when you're in a car and you're going over like a railroad tracks, and you can feel it by the seat of your pants. You can feel that the seat presses against you a little bit less when you're kind of cresting that hill that most train tracks have. If your town doesn't have a good train tracks with a nice little hill, my town has a really great one. And the first time the highway department tried fixing it, they actually made that hill be kind of sharp. And people going the speed limit were actually starting to kind of float over it and become little projectiles. So the highway department had to go out and make those ramps a little bit more smooth and reach out a little further so it wouldn't be such a sharp turn. But you can get to going fast enough that the car flies away and becomes a projectile. That wouldn't be the case for this particular problem because they say specifically that it's rolling over the top of the hill. I think that means it has to be in contact. Okay.
Joyce,
Yes.
we have a hand up, Anna.
Okay, Anna, go ahead.
Yes, I just wanted to ask, like, why did we have to have a negative sign over the centripetal force mv squared over r? I thought that we said that we display our coordinate system in such a way that r always points in the positive direction, of which in this case.
Oh, that's a very good question. That's a very good question. Because when I started this problem, I was using y as my coordinate system. And I was using the default. I didn't put it up here, so it's good for me to put that up there. But I was using y as positive, so n's magnitude was positive. Mg is the magnitude of the force of gravity. I put a negative sign because that's pointing down. And this centripetal acceleration is also pointing down. So this side of the equation has to be negative as well. If I had picked instead, perhaps for this problem, it would be a better coordinate system to use the r and the t this way. Then I would have had to write it. The sum of the forces in the r direction would be, well, Fg is along the r direction, so that would be mg minus the magnitude of the normal force, because the normal force is in the negative r direction, equal to m AC. Oh, just barely got that in. Okay. So your results should not matter, should not really depend on which coordinate system you use, right? But you just have to be consistent with the signs within the coordinate system you're using. Okay? All right. Well, I feel like we've done a whole lot. And then maybe I want to send you to a breakout room with a question. But let's do a little experiment. Now, I did this the other day with some people on a Zoom meeting, and I went and showed a video, and they told me the video came through okay. But I've got this, so I've got this video here, and it's called Chitose. I know it looks like it should be Chitose, but she pronounces it Chitose, and she's one of our LAs in Physics 118. And she's taking a course with me, Physics 300, which is the course that all the LAs take the first 2 times that they're LAs. And we talk about how to facilitate learning and so do a little bit about physics education research and how people learn physics in particular. But here, I have them do projects. And Chitose said, hey, for my project, I can make this video that's relevant to circular motion in Physics 117. And so she made this video and sent it to me. And so this is part of her grade for another course. But you're going to see Chitose around the Sophia Smith fountain. And what I think I want to do here is this. How do I do that while I'm in shared screen mode? I don't know if I can do that when I'm in shared screen mode. So I'm going to do this instead. I'm going to actually go get the YouTube link and copy that. Now, can I put this in? No, I'm going to have to stop my screen share for a moment. So let me stop the screen share for a moment and go into the chat. And I'm going to put that link right there and send it to you all. Okay, and then I'm going to go back to my screen share. Okay. All right. So there's a video there, and I'd like you all to just open that video up and take a look at it, and you'll see Chitose involved in some circular motion. And in that circular motion, I want you to specifically notice her body is not oriented, vertically upright the way normal people would walk. But she's kind of leaning in towards the statue, okay? And what I'd like you to do is think about that. See if you can draw a free body diagram for the situation. So task number 1 is draw the free body diagram. Task number 2, which I think is a little bit harder, see if you can use that free body diagram to explain why she's not walking vertically upright in that situation. Okay, so now this is going to be my first chance to put everybody into some rooms. Now, do I have any idea of how many people we have here in the Zoom room? Let's see. So there's 10, 20. Looks like I've got about 30 people here. Maybe a little bit more. And 2 of the people are me and my smartboard. So let me go ahead and I'm going to try putting you randomly into some rooms because I think that's the easiest thing to do. Breakout rooms, there we go. Let me make, since we have about 30 people, I'm going to go ahead and make 6 rooms. And when we get into those rooms, you'll see a note on your screen asking you to enter a chat room or a breakout room. And your room may or may not have an LA in it, or it might not have a faculty member in it. But you might, faculty member in LAs, we can move around. So I'd say go right ahead. Oh, hold on, I've got to, before I send you to breakout rooms, I've got to give Travis his special powers back. There we go. There you go, Travis. You should now be a co-host. Okay. So let me do those breakout rooms. You should see an invitation. I'm going to let you go to the breakout rooms, I don't know, for 5 minutes, and then maybe I'll call you all back to chat about the problem. Remember, your assignment is to get a free body diagram and see if you can use that to explain what's going on. Okay, I see Alex and Yarhead staying in the main room with me.
It'd be like wind drag.
Oh, hello.
Hi, just thought I'd pop in and see how you're doing.
Yeah,
Don't
we're
worry me.
we're just talking about because Joyce Joyce just shared with us, like what she wrote down, which was we are considering force of gravity and normal force, but we're talking about, oh, can you hear me? Did I cut off?
It's mostly.
Did it go through? Sorry, is my internet being weird? I got kicked out of my class earlier 3 times, so my internet's been iffy. But we're considering normal force and force of gravity, but we're talking about what other forces we might have to consider for this situation. But
I think there could be like a really small like wind force, I guess.
Air drag?
Yeah.
Like when
If
you're
she
running around.
runs.
True.
Also, how about friction?
Oh, that's right. Because she goes forward.
See, this might, I'm like thinking, because why isn't she completely vertical? Are we considering centripetal? Like that? So what would we consider for that motion? Wow, this is...
I feel like she's not, it's like vertical because there needs to be that, I guess, R component where she's to like get her to continue going in a circle. Because if she were totally vertical and there was no R component, then she would just go straight.
Yeah.
I mean, I think that we do have a friction force and an air drag force, though. So.
Okay. FG, FN.
All right, I might pop in on a different room now.
Okay.
Might be enough force. Not sure.
I'm just popping in to see how things are going.
Pretty good.
Yeah, I like the whiteboard. That's a great idea.
Thanks.
So that you've got like gravity pointing straight down, and then the normal direction is in this like angle, because then we know that F net is somewhere to the left.
Okay, so it looks like you've made some progress on a free body diagram. And I guess then the harder part of the question is, how do you use that to explain why she's tilted up? So I'm gonna go check into with another breakout room. Hi, just thought I'd pop in and see how your breakout room is going. You made some progress on a free body diagram? Oh, okay, so you've all agreed on a free body diagram and everybody's on board with it? What's it look like?
It's like kind of hard to see with the 3 axes, but like we figured there were like three identifiable forces.
Okay, so I see FG and I see FN kind of off to the side. And then what was the other force?
We said it was static friction because it was what was allowing her to keep running forward.
Oh, okay. And you're trying to, when you do that free body diagram, you're trying to do it like in 3 dimensions, right?
Yeah, that's
okay. So it looked like the like the normal force and the frictional force were not at 90 degrees from each other, but that's just because you're trying to do it like do it this way. My thumb's got to go down this way for gravity, and then there's a normal force, and then there's a perpendicular to it is where the static friction is to help her keep moving. So she's pushing against the ground, and that's how she's able to move. Okay, good. So how are you doing on the second part of the question?
Well, we thought that like if you took all of the forces along each axis and like added up, like if you took the components of the normal force, because it's like at kind of an angle, so it's not like right along the axis, but if you break it into the components and like add it to the other forces that were already like lined with the axes, then they would kind of like add up to 0 maybe, because then that would, or at least in the direction like where she wouldn't like fall over.
Oh, okay. So you're saying that this free body diagram should be balanced, that it should have a net force of 0.
Well, not in like every direction, obviously, because she has to be able to run forward. So like probably in that like the static friction, whatever like axis that's on, that would not be 0, but like
so that's the tangential direction, right? Right. Okay. Well, let's not worry about the tangential direction, because in the end, if we're thinking about this as like if she's approximately going constant velocity, then I'm not going to worry that much about tangential acceleration, and let's just think about it as constant velocity for the moment. And then, so it means we should focus on the forces that are sort of in the R and the Z direction. Does that make sense?
Yeah.
Okay. All right. I'm going to go visit another room.
Okay.
Didn't you just say, Jack, that the friction would be parallel and the normal's perpendicular, right? Or did I mishear?
Yeah. So that's just how it always is, right?
Mm-hmm.
So would that mean our normal force is wrong?
No.
Hi, Joyce. I couldn't get back. My computer froze, and so it kicked me out of the breakout room.
Let me see if I can get you into. There we go. Which breakout room were you in?
I think it was number 2. I'm not sure.
All right. I think I'm sending you there now.
Thank you.
Oh, you're welcome. Thanks for grabbing me. Okay.
Basically kind of like a ramp in a way. I don't know if that makes sense. Oh, hi, Joyce.
Hi, just thought I'd pop in and see how y'all were doing. I see you figured out how to share the screen of something so that you can draw. That's very nice. Okay. I'm thinking it might be that not everybody has answered all the questions, but everybody's got a free body diagram. So I might call us all back into the main room to follow up on this problem. Okay? So. Okay. More, and they'll kick everybody out of the breakout rooms. Oh, hey, Lucy, it's been a while since I've seen you.
Joyce, I think you might have been muted for a second.
Oh, okay. Hey, can you hear me now? Okay. Mm-hmm. Okay, so I think we must all be back in the main room. So I poked my head into, I think, 4 out of the 6 rooms, and what I saw, I was really happy to see people drawing nice free body diagrams, and I can tell you a little bit of what I saw, what kind of forces people were putting on their free body diagrams, and I'll do that up on the main board here. If we're thinking about Chitose being right here, oh, let me get myself back to being a pen. If we think about Chitose being like right on that sort of that curved edge there, so I'm going to dot that kind of curved edge on my free body diagram. That what I saw, everybody had gravity on their diagrams, and everybody had the normal force, and the normal force would be perpendicular to that surface. That's why I wanted to make sure I draw that properly. I've got a normal force, and some people had some other forces in there as well. This would be then in the if she's going around in a circle like this, then the R direction would be straight towards the center. So let me put in my coordinate system here, my R. The T direction would be kind of into the board, so I'm not going to draw the T direction, but that means this is now the Z direction, up and down, what we might have in other systems called the Y direction, okay? But everybody had these 2 forces in it. Some people had friction and some people had drag. And I'm wondering if anybody is willing to, let me pull up the chat and the participants windows so I can see. Does anybody have another force that they want to put on here, or some questions about what, what the heck is going on here? Okay. Okay, so I see static friction and air drag. And static friction is coming in. So yeah, you would imagine that's concrete that there should be some static friction. So my question for you is, well, what direction do you think the static friction is in? And I think the one thing we know for sure about static friction is it's perpendicular to the normal force. So it's got to be along this surface here, but it also could be that surface kind of goes into the board as well. So if we're going to have static friction, it's got to be in kind of some combination of those directions. So I'm seeing a lot of people saying static friction. And some are giving the direction that in the positive T direction, you should have some static friction. And that would be like each time she takes a step, she's pushing off. But each time she takes a step, eventually she lands on her other foot. Right? When she lands on her other foot, what direction is the static friction on her foot? There. it might actually slow her down a little bit. But then she gets over it and then pushes off again and speeds up. So I would say when she's running, it might be that it's kind of a wash. Like sometimes when she's pushing off of one foot, yeah, there's static friction pushing her forward. When she lands on the other, there's a moment when she actually gets slowed down by static friction, but then she speeds up again. Okay, so I'd say yes, in the T direction, there'll be some force due to static friction, but over time that should probably even itself out if she's going at a constant speed. So just to keep the problem simple, let's assume we're talking about the portion where she was going at mostly a constant speed around there, so that I don't have to worry too much about the T direction of the static friction. So what else is that? Where else could you have static friction and in this particular problem? Does anybody have an idea? Yeah, in the direction she's running, that'd be the T direction. Mm-hmm. Let's take a step back and say, what if Chitose wasn't running? That she was just kind of standing there, right? If she was standing there, what would it be like? Right? She'd be sitting there. She'd be on this surface. My guess is that she'd have to bend her knees or something to stand there. But if she's just standing on that surface, I would argue the normal force is still perpendicular to the surface, and that force due to gravity is pulling her down. And if she's not in circular motion, if she's really, really at rest, there better be something else holding her in place, otherwise she's going to fall down. So what direction do you think friction could be in this problem? Okay, up and to the right from many people. Good. So here we could have it up and to the right. Okay, and that would certainly be possible. How big does the friction have to be? Well, that's interesting because we know over here that eventually we have to have an F net that's in the same direction as our acceleration. So this force due to static friction doesn't necessarily have to be very big. And it could in fact be zero, right? If she's running perfectly at the right speed, she could have no static friction force at all acting on her along that direction and still get to be running around in a circle. So let's go to the second part. I'm going to leave that static friction force there for the moment, and I want to downplay its importance in answering the second question, that the static friction is not that important when it comes to explaining why her body's not vertically upright in this particular video when she's running. And she seems to be running kind of at the easiest point where she's not having to scoop her feet along to keep herself in place. Does anybody have an explanation they'd like to share regarding why is she not upright? Why is she comfortably tilted over like that? Okay, Piper, go ahead and pipe in, unmute your microphone, and then I'm going to call on Anna next.
Okay, so the reason that she's kind of at that angle is, I think, for two reasons. One, because the surface is at an angle to the ground, and for a second reason, even if the surface were completely flat, she would still make a little bit of a curve, like while making the turn. And I think that's because of like something from the textbook called it like a perceived velocity, or like a fictional force maybe. I think that her velocity and the shape of the surface is causing her to turn that way.
Okay. Let me go ahead, Anna. Or Anna, excuse me.
That's okay. Well, I think because we have a vertically downward force of mg that's acting on her, if she had a vertically upright force, then the two could possibly cancel because we don't have any motion in the y direction. So, because she's running around in a circle, she has to have an acceleration. That's like she has to have a net force that's directed towards the circle. And for it to have that component of a force that's acting towards the circle, then her normal force has to be at a certain angle so that it provides both the vertical component that balances mg, and then it provides a net force that's in the r-axis. Yeah.
Oh, okay. Yeah, I think it has everything to do with, like you were pointing out, the direction of the normal force. And kind of when you're loping around and it's easy and it feels like the person who's in that accelerating reference frame just sort of feels like their normal force is pointing down like it normally would, then part of that normal force is what's allowing you to stay in circular motion. I think we may not get to the definitive answer on this particular question because I feel like we're running out of time. We're kind of already at the 2-hour mark. But this is the kind of question that I hope makes you wonder about things and then how we describe things. Let me see. So there's a couple more problems I'm willing to stick around for, but I understand if people have other things they have to do because we're getting to right about, it's almost 3:10 at this point. But what I would do then instead is I would point out that there's a few questions on the blog. And one that I would really like everybody to take a look at, whether you do it here with me now or later on, is this one. You might recognize this turntable here that was in the classroom. And this turntable definitely has 2 little coins on it. It has 2 quarters on it. And this was just a clear plastic plexiglass piece that actually Jack made a few years back for a Physics 300 project. And I don't know if you can see very well, this axle in the middle, it has a little string wound around it. And that string comes off the side, and there's a little bean bag over here for mass. And when I let go of the table with my fingers here, it's going to allow that mass to fall, and that turntable is going to start spinning. It'll speed up slowly, so I'm not so much worried about the fact that the RPMs are changing. But I've got these objects on a turntable, and let's suppose it has each of those objects has a mass. They're at distance r from the center. One has a smaller r than the other here. There's a static coefficient of friction for this table and these little bits of metal. And I'm going to let omega for the turntable increase gradually. So the question is, at what value of omega will the object slide off? So let's actually look at that problem together for a moment, and let's build the three-body diagram together, and then maybe I'll send it to breakout rooms to answer some questions about it. Okay, so what I'm imagining here, let me draw out a little bit. There's the center, there's kind of the circle, and I've got one of my coins sitting right here, and that this would be the R direction, this would be the Z direction, and the T direction would be, into the board there. And I'm not going to worry that much about the T direction here. If I were to draw that free body diagram, can anybody tell me one force that should be on that free body diagram? And go ahead and unmute your mic and shout it out.
Gravity.
Oh, of course. So I didn't catch that though. So Joyce.
Gravity.
Gravity. Oh, good. Because I say, if you get the first choice, always pick gravity for the free body diagram question, right? So force due to gravity pulling down. Okay, what's one other force? Somebody else.
The normal force.
Normal force is that platter, that plastic plexiglass, and I'll make it Fn here, just change my notation a little bit. Okay, are there any other forces acting on it? Another, somebody else?
There's gotta be static friction.
There's got to be some static friction there. Yeah, so whenever you have a surface, you always potentially have friction and a normal force. We've drawn the normal force. What direction would the static friction force be if it's turning, if this turntable is turning, I'll just say it's going to turn this way. And that was, sorry, that was a little bit of a trick question. So how, yeah, so how do we think about what direction that the static friction should be in? There's sort of two ways to look at it. And I think in this case, the easier way is to look at it from the point of view of forces. And the only other force I have a chance of here is static friction. And I know from my motion that the acceleration is going to the left. So I know over here in my free body diagram that my F net has to be to the left. Has to be, because it's going in a circle this way. So static friction's got to be along this surface perpendicular to the normal force. So if we put it there, that would at least make sense, given the physics and what we know about the motion and what we know about the acceleration. There is another way of looking at it to say what direction would the object slide and so on. That's a little harder to do in a circular system, and I'm not really ready to do that over the internet. Something I can do much better when I'm in the room with someone. But let's take this as our free body diagram. And now we can say that we would just write our Newton's second law equations. In the z direction, it's a little boring because here the normal force is just equal to mg. But let's look in the radial direction. So the sum of the forces in the r direction, and here I've got r direction going to the left. So I'm going to count the force due to static friction with a plus sign. There's no other forces in the r direction. Let's let that be mass times centripetal acceleration. Since my question was posed in terms of omega, maybe I'll put that over here, m omega squared times r, okay? So what is that telling me? It tells me that the force due to static friction will support this motion, this circular motion at angular velocity of omega for a particular distance r from the center. So if it were going really, really slow, you wouldn't need that much friction to accomplish this centripetal acceleration, right? If we're going really, really fast, then this centripetal acceleration is going to be bigger and bigger and bigger and bigger. Can we supply an infinite amount of friction? Not if it's static friction. There's going to be a limit, right? So let's think about that limit. Okay, and this, I think someone had asked about this critical velocity versus angular velocity, and this is where it comes in. That static friction has a maximum value, okay? And therefore, and this is the important part of the thinking about it, therefore, omega times squared times r, oh, I left out m, times m, that in order for it to stay in circular motion, has a, let's say, I won't say uniform, but for circular motion, also has a maximum value, okay? All right, so this quantity on the right-hand side has a maximum value because this quantity on the left-hand side has a maximum value. Okay, oh, so if I go a little bit lower and maybe extend my page a little bit, we can get to one more line, and then I'm going to send you to your rooms. That if we're just thinking about that maximum point where we're at the maximum amount of static friction, well, that would be mu s times the normal force. That would give us, let's say, omega max squared for a given r. So if we're thinking about the problem in terms of this is going to speed up and speed up and speed up, well, there's going to have to be a maximum speed. All right. So my questions for you are, actually, they're all laid out on the blog as well. So, okay, let me do something. What I want to do is I want to put the link to the blog actually into the chat. Oop. So grab that and copy it. I'm going to have to briefly go out of the screen sharing to do it. Let me go in the chat and send this to everyone. There we go. Okay. So I just sent you all a link through the chat. And so what I'd like you to do is click on that link. You'll be sent to the blog where you may have to log in. When you're I'll go back to sharing the screen. There we go. One. Okay, so now you can see my screen, which I've got the blog there. Let's see that same picture we just talked about. But if you go a little bit further down, you'll see 3 questions. There's a question about the 2 quarters that we just talked about. There's a question about 2 objects of different masses, and there's 2 disks, one that has a bigger surface area than the other. So what I want you to do when I put you into your rooms, what I'd like you to do is try to answer those 3 questions about which object is going to fall off first, given that they're on a platter with the same omega. And some cases the R is different, some cases it's not. I want you to take a look at those questions together and see if you can explain, using what we just talked about, why the videos work out the way they do. Okay, so I'm going to go put you in the breakout room. I think we have fewer people. Options. Let me recreate those. I'm going to take it down to 5 rooms because we've lost a few people. Yeah, let me do that. I'm going to recreate the rooms and then open up the rooms. So head to a breakout room and we'll talk about those 3 questions, and that'll probably get us to close enough to 4 o'clock. Is there something wrong?
So am I supposed to work 110 to 310, or is it?
Oh, well, if you can stick around, we can work until whenever you're done. This week, I had no idea if people would stay after 3:10, but I think some people do need it. So if you can stay, fine. If you need to go, that's fine too.
I have another class.
Oh, you have another class, so you definitely go for that then.
Okay.
Okay.
Cool.
All right.
Just like,
See you later.
thank you. See you later.
Hi, just checking in. I know your breakout room is small because it randomly put the Save and Read Save and Read Smartboard in your group.
Oh.
So you guys, so have you got, thought about any of these yet, or you're still working on it?
Yeah, I'm still like reading the questions.
Okay, alrighty. I'll head out. I'll come back and check in later.
Okay.
For the free body diagram,
Yeah.
I think they all have kind of the same free body diagram.
Mm-hmm.
Oh. Doesn't the static friction always stay the same though? Like the magnitude of that?
Maybe not, because it's affected by the radius.
Yeah, but like the static friction coefficient never changes.
If they're from the same material, it wouldn't change.
Yeah.
Radius, then it would affect the static frictional force.
I think it'll affect the how fast it can like. I don't think it'll affect the force. It's just that the omega has to kind of like decrease.
Yeah, I'm kind of. Okay.
So the static friction is less on the one that's farther away, right? Because it's being divided by 2r.
Yeah, and I guess
Yeah.
that makes sense, because if it's like farther out, your the acceleration is less, and so like you would need less of a static friction force to like keep it from falling off.
Right. And so then, yeah, I would say that the one that has less static friction would fall off first.
Yeah.
Which would be the one that's farther out.
Wait, sorry. Okay. So you guys said the inside coin has less static friction?
No,
Or
it would have
we
greater
said the-
static friction.
Okay, so the one on the outside has less.
Yeah.
Yeah.
Oh, because it has a bigger radius. Okay, that makes sense.
I know it's in here a little bit.
That's why like drawing out the formulas is nice, because you can see that it's being divided by 2r.
Yeah.
Okay.
Just poking my nose in real quick and listening in on the size of the static friction force, and I think you're doing great by looking at the equation and saying, well, you know, if those velocities were the same for the coin that's at a distance r compared to the one that's at 2r, if their velocities were the same, then you could certainly say that the one with the larger r would have the smaller static friction force. So my question for you is, are the two velocities the same in this experiment?
I want to say no, because like if this one has a larger, if mass 2 has a larger radius from the center, then it's like traveling more distance every second than the one closer to the inside.
Yeah. Is there anything that, as far as velocity goes, that they do have in common? Like
I guess
don't
like
just
the
have-
angular velocity would be the same.
Oh, their angular velocity might be the same. So it might be better to set up your comparison in terms of omega rather than v, given in this for this particular problem. Now it might be there's another problem where they have the same v, and this comparison would be great. But I didn't want you to get too far down this road because everything else you're doing was great. Okay, so I'm going to go check out another room and leave you guys to keep going.
Oh, you're right.
But also, if it's lighter, because when we're talking about the static friction value is going to be different as well.
Mm-hmm.
So for the y component, the normal force is equal to the gravitational force because it's not accelerating, which is mg. And then for the static friction force, it's mu Fn, which is also mu mg. So don't the masses cancel out?
Would they? Wait.
Like this.
Oh, okay. Now I see what you mean.
So in that case, it would still be affected with
Okay.
But I'm happy to see you've discovered that I didn't do all the work for you, that you had one more step to take in figuring out this, this equation. I left you one step short of the final, more useful formula that might help you sort out the rest of the questions. So very good. I'm very happy to see that. I'm going to go visit another room now.
Okay.
Oh, Joyce, you're muted.
There we go. Now I'm unmuted. Okay, thanks.
Yeah, so we rewrote the formulas according to omega and determined that the object that's farther out would have a greater static friction, and so we thought that it would fall off. It would fall off second, and then we watched the video, and that was not true. It fell off first.
Yeah, yeah. So how did you get to the reasoning that it would fall off first? Because because why? You've got said the force due to static friction is m times omega squared times r, right? And they both have the same omega.
And different R's.
But they have different r's. Okay. And in a way, that particular equation, let's see, am I allowed to write on it?
Yeah.
I think so.
I don't know. We'll see. View options, annotate. I guess the one thing that I would say is that it's not if we're thinking about right when it's going to fall off, let's just talk about when it's going to fall off. That the force due to static friction, the maximum value that's equal to m omega squared. Sorry, I'm not going to be able to do omega squared times r. And I'll just put a little space between them, right? But this would be then, if that's the maximum force due to static friction, then this is the omega max. So I just wanted to put like max here on your FSF and the omega squared. So if we look at that, we could solve that for omega max and see which object for the same maximum static friction force, and they're the same mass, right? How would that vary with R? We could look at it that way. Does that make sense? Yeah, I see there's a lot of people that are kind of stuck at this same point in some of the rooms. So I might, maybe I'll just go around room to room. But here, could somebody go ahead and do the algebra to get omega max on one side of the equation and get everything else on the other?
It's so hard to write.
Yes, it is, isn't it? Okay. So looking at that equation, the maximum speed for which that coin is going to stay on, is that maximum speed bigger for the one that's further out, or is it bigger for the one that's closer in?
It's bigger for the one that's closer in.
Yeah, so it's going to be able to stay on longer. If its omega max is bigger, then it's going to be able to stay on longer than the other. So so I completely understand the road you took to get the other conclusion too. So just be really careful about what's the thing that you're trying to compare to. And now I think you're in a pretty good position to do numbers 2 and 3. Just remember that that is technically that this is SF max here, okay? And that's important because the model for friction only tells you about the maximum force due to static friction. It looks like I said F may, but I really mean max there. That's the only time you can use the model for friction. And you can substitute things in like mu times Fn, and the normal force is related to mg, you can put that in as well. Okay, does that make sense?
Yeah.
Is there any other questions before I go check out another room?
So this is assuming that they have the same static friction or max static friction? Or we only focus on the radius?
Okay. Well, for question 1, you are focusing on the radius. But the one thing that you do know, let me go back to annotate there. And I do a little bit better typing than writing. So I'm gonna do it with text. The one thing you do know, right, is that F for static friction max is mu s times the normal force, and in this case, the normal force is mg. So that mu is together, mu s times m times g, right? And the second m is mass then, right? So that may help you sort out the problems with the coming ones, which have, in one case, different masses. So I wanted to just point that out before I left the room so that works itself out. Okay?
Okay.
Do you have any other questions before I go check into with another room?
No, we're good.
Okay.
I'm gonna be right back, guys. I gotta grab my charger.
Important question is, does static friction depend on mass? No.
Does static friction depend on mass? Well, what's the static friction equal to?
Maximum. It's mg. It's coefficient of static friction times the normal reaction, which is mg. At least in this case.
Yes, I'd agree with that.
Oh, okay. So it means that as the mass increases, then static friction is also going to increase the mass.
As the mass increases the static friction, I would.
I thought I'd come by and check in on you guys. You're looking pretty tired. I know it's been kind of a marathon here. Are you ready to come back to the main room? Maybe I'll call people back to the main room. Okay. And you are always free to come back to the main room. There's a few people there discussing things that are on the board, and maybe I'll continue the work on the board as well.
How do you come back to the main room by yourself?
By yourself? Oh.
Well, like, I mean.
I will force you all back to the main room if you don't find your way, okay?
And that'll be equal to what?
The static friction, right?
Mm-hmm. What happens to the m's?
Oh, they'll just cancel out.
Yeah.
Oh, I see. Okay. So it doesn't. So it doesn't matter.
Yeah, but the R stays, and that's why it was different in the first case.
Mm-hmm. Okay, that makes sense.
Okay. Yeah, I believe that's the case. Joyce, do you have anything you want to add?
No, I wasn't paying enough attention to add something, but I am going to invite people to come back to the main room because I think partly because people are kind of tired and many people are stuck on the same place. Some have gotten past it, but I think we'll gather everybody back here in about 1 minute. And I think it sounds like you guys just made a little breakthrough, which I'm really happy to hear.
We did.
Okay, so I am closing all those breakout rooms, so people should be heading back here. All righty. How are we doing? Is everybody back? All right, so we have fewer and fewer people because it's getting late. And I kind of sense it was getting kind of late and people are kind of tired. And I did something that was, I don't know, maybe a little bit not nice, but I wanted to be in character. I'm not always nice. I left a little bit of algebra for you to do here. So let's go up to the main door. And many of you figured this out, so I'm very proud and happy about that. Is that here if we restrict ourselves to the moment that something is about to slide off, we can use this equal sign and we know how big the static friction is. And in this case, the normal force was equal to mg. If you go back and look at the free body diagram, you can also convince yourself that that is the case. And then we get m omega squared. And I'm putting in max here because this is the maximum, this one that gets you to, requires the most friction, times r. And you see mass is on both sides of this equation. So I can divide by m on both sides. And I'm going to do two steps at once. I'm going to divide by m, and I'm going to also divide by r. So r comes over to the other side. So mu mg divided by m times r, and those cancel out. That would give me omega max squared. And taking just one more extension on my page here, that means my omega max is square root of mu times g over r. Now this is the simpler form. And I think if I'd sent you to your rooms with this instead, then it might have been a little more straightforward about that first race. Now in that first race, which of the two quarters falls off first? How could you predict that? Well, one of them has a bigger r. So the one with the bigger r, would its maximum rotation velocity be bigger or smaller? Well, it's in the denominator, so it actually has a lower speed limit. So if that turntable's omega surpasses a certain amount, it's going to fly off. Compared to the one with the smaller r, that makes this whole piece bigger. It's got a bigger omega that it can withstand, so to speak, before it will slide off. So if you watch that video, I think you'll see the quarter that's on the closer to the outer edge is the one that falls off first. And I think many of you got to the point of looking at that and either having a good prediction beforehand or a opposite prediction. The important thing here, though, I want you to notice, is that mass canceled out. I mean, mass was in the numerator and the denominator, or if you look at it up here, mass is on both sides of the equation. So sure, a heavier object has a bigger maximum force due to static friction, but the bigger object requires a bigger force due to static friction to keep it in place with the acceleration that you want for circular motion. So since mass is kind of evenly on both sides of the equation, that second video we should say, well, mass shouldn't matter. So for the first video, this equation is helpful. For the second video, realizing in this step that mass is on both sides of the equation, we should say that mass doesn't matter. That would be one way to look at it. Mass doesn't matter. And you know, that's not intuitive. I don't think that's obvious at all from looking at the situation physically. Okay, so that's actually a big, kind of a big thing. Oh, I realize my chat window's not open. Okay, good. And I think we're just about done here. This similarly for number 3, surface area. Is surface area anywhere in here? No, our model for friction does not account for anything with surface area. And to a good degree, most systems, the surface area doesn't matter. Now, does it matter if you were sitting there, would the thing with the smaller surface area, would it hurt your hand more? Yes, it would hurt your hand more because of the pressure, because that force is spread out over a smaller area. And maybe in the extremes of like extremely small areas, it might make a difference. But our model for friction doesn't cover that. Our model for friction says that area doesn't matter either. Okay, so I think everybody is way tired and ready for a break. So the last thing I think I would do is let you know that on the blog, there are a couple of more videos having to do with loop-de-loops and with driving sideways. It's a little bit like the Chitose problem on steroids. There's some videos and some thought questions there. The other thing I would, we're not gonna have time for the conical pendulum, but maybe I can post that as another question. The next time we meet, it's going to really be kind of your choice what we do. There's Chapter 7 and Chapter 8 problems that are posted in the PSS section. And I also posted some what I would call short and sweet Chapter 8 concept questions. So those are also on the table for discussion at our next meeting tomorrow. The problem solving sessions are normally 4 to 5, but we expanded, come early if earlier works for you, stay later if that particular time works for you as well. So we'll start with things that are posted on Moodle tomorrow and try to work problems in small groups and somehow manage our breakout rooms accordingly. Okay, that was a lot. Are there any questions that people would like to ask before we end the meeting here? I'm going to unmute everybody so you can just shout it out.
Are all the problem solving sessions, are they going to be kind of like how we solve problems today where we all break into smaller groups and just stay in those groups?
We can do it that way, but I'm willing to be as flexible as this technology is able to let us be. Today I assigned them randomly, but since I'm the host, or when Travis is there, he's the host, I have superpowers, and my superpowers include being able to put people into breakout rooms that I assign. So if you were to show up and someone else were to show up, say, Piper showed up and Theo showed up and you guys wanted to be partners, I'm happy to put you in a room by yourself, but if you wanted Leslie in there with you, I'd put Leslie in there with you. I can take special requests, or if you show up and you don't know somebody, I can introduce you. And you're always free to move in and out of the breakout room into the main room. I would have to move you from one breakout room to another breakout room. And then the LAs and the instructors have the power to move among the breakout rooms as we go. Does that make sense?
Yeah.
Cassandra, do you have a question?
Not right now.
Okay. Does anybody else have a question here? Go ahead and shout it out.
So the weekly homework problems, will it be on what we just covered today?
So weekly homework problems, there's actually 4 of them there. 2 of them are from Chapter 7 material that we did the previous week, and 2 of them are related to Chapter 8 material, which we reviewed a bit today. We didn't, I wouldn't say we covered everything, but we're by, I think, definitely taking a look at those problems and bringing questions is going to be perfectly fine on either Tuesday, Wednesday, Thursday to any of those sessions. In fact, I recommend that. Somebody was in my office the other day and I told them there is, no force stronger than a woman with a question that she wants answered. And I count you all in that group of people who will just keep pursuing the question. So once you've got a question, there's no stopping you. You're going to be able to get to the point of understanding something. So absolutely take a look at things in advance and come with questions. And it may be you'll feel you don't need to stay for the whole time period if you've done some work outside. But I think in the end, the amount of time you put in is going to be the amount of time you put in, whether you do it while we're together on Zoom or whether you do it when you're working by yourself. I do recommend, if you're working by yourself on something and you get stuck, write down the question and move on. Okay, write down the question, because then you can come in, ask your question and get unstuck. Move on and try another problem, or move on and try some other thing. Don't spend any time banging your head against the wall. You spend a little bit of time wondering about it and questioning yourself about it. But at some point, write down your question and put it aside. And I guarantee when you come back to it later, you'll do better. Okay? Does that make sense? Okay, Jackie? Oh, I just didn't know if Jackie had a question.
Oh, no, I was just, yeah.
Okay. All right. Well, everybody, I know not everybody's here, but Gokudo Samadeshita. This was hard. We're all doing something that's hard. So if you feel tired right now, that's the way you're supposed to feel. Everybody, get a night's rest. And I'll see, I think, many of you tomorrow and many of you Wednesday as well.
Okay.
All righty. Bye-bye.
Bye.
All right. Oh, I'm exhausted. I don't know about you.
Yeah, I'm tired.
Yeah.
A lot of
Yeah. So I definitely have a different class. And I think there's a couple different places where I might have done better setting them up for things, but hopefully I'll get better at that.
Yeah, I mean, I thought it was fine, good. It was valuable for me to just kind of experience what you experienced this morning of like sort of being there and actually being able to pay attention to the chat and going into the breakout rooms and hanging out with the group for a little bit. That was enjoyable and kind of just valuable to see what that looks like when I'm not hosting and trying to coordinate everything. So
yeah,
a good experience. And just the view is different in some ways, like that I know you already appreciate, but like it was nice for me to see what it looks like when you are sharing the screen, and I can go into this mode where I can like, choose one of the videos to look at next to the
right. And I realize that it's kind of different because I sort of have the screen I want to share is separate from my video window, and I'm not sure I like that as much as this morning where we had figured out how to pin one video and put the shared screen on one side. I don't know. I'm trying to decide whether it's really worthwhile. I didn't find the classroom being as big a benefit as I thought it would be, I guess. I should probably, actually, I'm going to go ahead and end the recording. That's probably